So I would like to talk about aberrations in holography, and I start off with aberrations of lenses to give an introduction to aberrations in general, and then I go on to the analog model of I go on to a holographic model of aberrations, and talk about aberrations in holography. And I derive some equations to show what the aberrations are, and then we get some implications from those equations. And then there is an experimental demonstration of some aberrations. So in a perfect lens system, you have an object plane here and an image plane here. And in a perfect system, every ray from the object goes to its corresponding point in the image. In general, this is not true. In general, the paraxial rays very close to the axis will do this. The extreme and the marginal rays will generally be aberrated. So an aberration in an imaging system is defined as any aberration of an image due to imperfections in the imaging system which are inbuilt into the system itself. In standard optics, these occur for non-axial object points, points that are slightly above the axis of the lens, and for these extremal rays coming off of these things. Note that if you have a lens and an axis and a point on the axis and the lens is twisted, the point has now gone off axis, and so a twisted lens gives the same set of aberrations for a non-axial object. So the 5 standard aberrations are known as the Seidel aberrations. These are the spherical aberration, the coma, the astigmatism, Petzval or field curvature, and distortion. Spherical aberration occurs when the paraxial rays focus onto what's called the Gaussian focal point here. The marginal rays focus at a different point, and they may either focus closer or they may focus further on. The distance between the Gaussian focus and the extremal ray is the lateral spherical aberration. The distance between the marginal focus and the Gaussian focus is the longitudinal spherical aberration. Coma occurs because different segments of the lens give rise to circles. This part of the lens will take an image point an object point off axis and create a circle that is slightly higher than the Gaussian focus. As you get nearer and nearer the center of the lens, the corresponding circles become smaller and smaller until at the center of the lens, the circle has a radius of 0 and becomes the focal point at the Gaussian focus, so that an off-axis point here, the marginal rays will cause an image that is blurred in the shape of a coma, hence shape of a comet, hence coma. With astigmatism, as you go further off axis, you have 2 different foci. The light going in a plane that contains the object and the optic axis, the transverse plane creates an image there of a line. The plane across the lens creates a sagittal focus. So a point gives rise to 2 line images at right angles to each other and at different positions along the principal ray from each other. In field curvature, an object, a planar object here gives rise to a curved image. This is because there is a line, an imaginary line inside a lens that is considered to be normal to the axis at which the refraction begins to occur. However, as the lens gets larger and larger, this is no longer a line, this is a slight curve, and so the image itself becomes curved. Towards the paraxial region, a small straight line will give rise to a small straight line. As the object becomes larger, the curvature becomes larger. And distortion is because the magnification, the diagonal magnifications are different from the magnifications are perpendicular and along the axis. So you have pincushion distortion here and barrel distortion here, where the magnification is less. So in the wave picture, the way we describe these is that if you have a Gaussian focus here, then you have spherical, circular light focusing into that point, and this would be an ideal focus. But a real wavefront does not go along the ideal spherical wavefront except in the paraxial region. The further away you go from the axis, the greater is the difference, and that difference is denoted by W, which is a measure of the aberration. And W can then be given by the Seidel aberration equation. Each term in this equation represents a particular aberration. The first three terms are spherical aberration, coma, and astigmatism, and these cause a blurring of the image. The next two terms, the field curvature and the distortion, cause a distortion of planar objects. So in the holographic model, in order to show a correlation between holography and conventional lenses, it's necessary to create an effective focal length to the lens. To do this, we need to determine an equivalent focal length for the hologram. This could be done if the reconstructed hologram gives rise to a spherical wavefront and images to a single point. So for holography, we have a point object which, when reconstructed, gives rise to a point image. And once again, the point object gives rise to spherical wavefronts, which the hologram converts to an image of spherical wavefronts. And so the difference between the actual wavefront given by the hologram and the ideal wavefront of the hologram should be given is once again the aberration. So the program to carry out this task was first initiated by Meyer and then followed through by Champagne. We set up a coordinate system in which the hologram is in the xy plane with z equals 0. We have 3 points, O for the object point here, R for the reference point, which makes the hologram, and then we reconstruct that from a point C, which is not the same as the point R. So these 3 points have associated coordinates, xr, yr, zr, xo, yo, zo, and xc, yc, zc. And we start off by assuming that, we also assume that the reconstruction wavelength is not the same as the recording wavelength. So we create the number mu to reflect this. Mu is the ratio of the reconstruction wavelength to the recording wavelength. We then derive the wavefront on reconstruction and determine the difference between the reconstructed waveform and the actual waveform, and that difference will be the Seidel aberration. The derivation starts by calculating the phase of the actual wavefront coming off the hologram. The wavefront that comes off the hologram is a combination of the reconstruction wave, the reference wave, and the object wave, the original reference and the original object. So what we'd like to do is we'd like to say that if there is a circle, a sphere that comes off that point, and wherever the plate is, that point of light will create a specific phase at the plate. And that phase, due to some general point G, at some where the plate is at X and Y, that point will create a phase of that. So what we then do is to substitute that general circular phase into each of these 3 terms and create the actual wave that comes off the hologram. When we carry out this analysis, we determine where the image point would be from the actual wave that comes off the hologram. We get these 2 terms. We get the image point, capital Xi, and there's a capital Yi, which is the same as the X's, except you substitute for Y for X, and capital Zi. So these are the actual image points that come off the hologram, which may or may not be the original points. Also, there is as a slight test of this, if the point C, the reconstruction point, is the same as the reference point, then capital Xi should be the same as small xo. The image point should be the same as the original object point, provided that the wavelength change is 1. There is no change in wavelength. And this does do that. So there is an additional check on this, that you recover the object point from the image point if the reconstruction is the same as the reference. In order to create this lens formulation, this lens equivalence, you can then create the object point here, the image point here, and you create an equivalent lens focal length f, which from those previous equations comes to this. You compare that against the standard lens equations, and Champagne uses the same formulation. Champagne gets this, and you can see that this formulation, Champagne, is the same as this formulation, Meyer. Champagne was basically concerned with non-paraxial imaging, but he gets a very similar formulation for the distance of the object point from the hologram. The resolution of a hologram is not the same as the resolution of the holographic image. In that sense, the holographic image is a diffracted light field. We need to find the resolution of the image. We need to determine the resolution of the image in terms of the size of the source. To do this properly, you need to take the Van Zytse-Seneca theorem, and you need to determine what the spatial coherence of the source is with respect to the plate. But we can do a simple back-of-the-envelope calculation with what we've already got, because the rate of change of the image point with reference to the rate of change of the source size gives us this for the longitudinal and the lateral resolution. So there's almost a quick and dirty method of getting resolution. So having got those equations, we can then expand to a first order, and we can derive magnifications. There are 3 different kinds of magnifications: the transverse magnification, which is the height above the axis; the longitudinal magnification, which is the extension along the axis; and the angular magnification, which is the angle subtended by the object as it comes closer and further away. For transverse magnification, 3 interesting facts occur. First of all, if there is no change in wavelength between the recording and the reconstruction wavelength, if mu equals 1, and the reconstruction distance is the same as the reference distance, in other words, if ZO equals ZR, there is no magnification. The magnification is unity. So if you reconstruct with the same wavelength from the same position of the reference, there is no magnification. So this is a quick check on the magnification equations. If the reconstruction beam is collimated, if ZC equals infinity, then the only term with mu, that term, disappears. So there is no magnification of an image by change of wavelength if the reconstruction beam is collimated. There is only a change in wavelength for different wavelengths if the reconstruction is diverging or converging. A collimated reference beam will result in unit magnification. There is a factor of 1 over mu difference between conventional magnification and holographic magnification. There is that factor here, so that the lens metaphor is only valid insofar as the reconstruction wavelength is the same as the original reference wavelength. So this shows the limitation of the lens metaphor for the hologram. The hologram is equivalent to a lens insofar as there is an equivalence of wavelengths. For longitudinal magnification, in conventional imaging, the longitudinal magnification is the square of the lateral magnification. In holography, there is a 1 over mu factor here, which shows that even if if you change the wavelength, even if the transverse magnification is unity, if there is no change in the transverse magnification, there will always be a change in the size longitudinally. So that if you change the wavelength, the object will always extend further out. Angular magnification is independent of all the parameters of recording and reconstruction and depends only on the wavelength change here. Expanding that phase difference to third order gives the third order Seidel aberrations for holography. Again, the difference between the ideal reference and the real reference, and the ideal wavefront and the real wavefront. So we get this, so we take the wavefront and we take these parameters, the distance along the radius of the wavefront, the distance of the axis, the azimuthal angle, and we get a set of equations for holographic aberrations. So for a holographic aberration, this is the spherical aberration, the coma, the astigmatism, field curvature, and distortion. For coma, if both ZC and ZR are infinite, in other words, if both reference and reconstruction beams are collimated, then spherical aberration becomes 0 for mu equals 1. Thus, if the hologram is reconstructed with the same wavelength as the original reference, and both reference and reconstruction are collimated, spherical aberration disappears. Sorry, that was spherical aberration. For coma, if both reference and reconstruction beam are collimated, then the ratio XC to ZC and XR to ZR are used as tangents of the angle, because when you're collimating, there's no source for these beams, so you use the angles of the beams. Coma can be made to disappear if both reference and reconstruction beams are collimated and the object is directly in front of the medium. This results in tan theta equals 0, and it also results in the fact that the tan of the reconstruction angle must be modulated by the ratio of the wavelengths. Thus, if C and R beams are collimated, the coma may disappear if the tan of the reconstruction angle is modulated by the ratio of the wavelengths. If both these wavelengths are the same and the reconstruction angle is the conjugate of the recording angle, with both being collimated, coma can be made to disappear. In addition, if the wavelengths are both the same, the condition on the object position vanishes. So if you don't change the wavelength, the object can be anywhere you want it to be. If you do change the wavelength, then there is a condition on the object that it must be in front of the plate. Same conditions occur in astigmatism and in field curvature. However, if in terms of the field curvature here, the Petzval curvature, if the reconstruction beam is not collimated or if the ratio of wavelengths is not 1, then you will get field curvature, and the object and a planar object will be seen to bulge outward in a spherical manner. So these are experimental results. We used this image and we recorded the hologram at 514 with the object directly in front of the plate at a distance of about 13 inches. And the reference beam came in at 30 degrees. We reconstructed the hologram under a variety of conditions. We kept the reconstruction beam collimated while varying the angles on either side of the recording angle. We varied the beam divergence, and also we varied the angle. So we diverged the beam along the line of the original divergence, and we changed angles on either side. When we changed the direction of the recording beam and kept it collimated, the image moved, and you can see there is coma, the coma is greater along the direction of motion. When we diverge the beams, the object shrunk and moved in closer to the beam. You see the longitudinal change in magnification there. When we change the direction of the divergent beams, the object moved along an arc and also distorted in a circular manner, so that over here, the center here is very difficult to focus, but the focusing gets worse as you go out to the side, because the object, even though you don't see it, there's a curvature to the object here. And there's a whole series of photographs we took which just shows that. We did the same thing with the 633, and we got the same results, except that the image got bowed, and so it was impossible to focus the image at any point along the 633 when reconstructed with 633. So the best practice is to always reconstruct a hologram with a source that matches the construction geometry to include avoiding aberrations within the reconstruction force. When the aberrations occur, then understanding the effects will aid in troubleshooting the system. Thank you.